Hi, this lesson is about extreme values and what their meaning is and how they apply to graphs as well as critical points. So let's talk about extreme values first. So there's a lot of vocabulary that might be new to you. So an extreme value will be considered to be either a minimum or a maximum value of a function. These are also called extrema if we're speaking in plural, or extremum if it's singular. The process of finding an extrema is called optimization, and optimization will also be important in general throughout this entire chapter. So, an extrema, meaning a maximum or a minimum value, can be found either on the domain of an entire function or on an interval of the domain. So, if c is a value in some interval, f of c is an absolute minimum of f of x on that interval if f of c is less than or equal to f of x for all values of x in that interval. So all that's saying is that if c represents an absolute minimum, f of c will be the smallest value overall for all of the f of x's on that interval. So that's what this statement is saying. Similarly, if c is on some interval, f of c is an absolute maximum of f of x on the interval of I if f of c is greater than or equal to f of x for all x on that interval. So that means f of x would have to be the largest value, or equal to means that you might have more than one absolute maximum, just like above, or equal to would mean that you would have more than one absolute minimum. Okay, so just a little bit of vocabulary. Right here, I wrote that an absolute extrema is the same as calling it a global extrema or a universal extrema. So for the most part, I use the term absolute, but you might read in a different book or see a different video where they might refer to a global or a universal max or min, and it means the same thing. So there's a theorem associated with this. It's called the extreme value theorem. If f of x is continuous on a closed interval from a to b, then f obtains an absolute maximum value f of c and an absolute minimum value f of d on some interval, for some value c and d within that interval. So the extrema can be either the function values at the endpoints, meaning f of a or f of b, or some values in between. So right here, I'm stating that if you have an open interval, a, b, well, the extreme value theorem doesn't necessarily apply, so you might have no extrema. So an example of something where extreme value theorem would apply, here I have a, and here I have b, and remember the function is continuous, which means you can't have any infinite discontinuities, no jumps, no removables. It has to be continuous all throughout. So here's something that would apply. So here I would have a value c where I have an absolute maximum. And here b, which is the endpoint, is the absolute minimum. Okay, so you can have absolute maxes or mins at the endpoints of the interval, either at a or b, or they could exist somewhere in between, which we call c. And if you had another one, I would call it d. So that refers back to what was stated in the extreme value theorem. Okay, so in addition to absolute extrema, we also have something called local maxes and mins, or local extrema. So I'm right here. So a function f of x has a local minimum at x equal to c if f of c is the minimum value of f on some open interval in the domain of f where containing c, where c is an element of a and b. A function f of x has a local maximum. So I'm here, a local maximum at x equal to c, if f of c is the maximum value of f on some open interval where c is in a and b. So similar to what I stated above, there's lots of vocabulary associated with this. So local extrema and relative extrema mean the same thing. And so I usually use the word local. Sometimes I use the word relative, but you will see either one in other textbooks or videos. So let me illustrate all of these definitions in the picture below. So I have a function indicated here by this red curve, which is defined from A to E. So this is, let's say, some function f of x on the closed interval from A to E, and it certainly looks continuous. So this would definitely satisfy the requirements of the extreme value theorem. Now, this particular curve has both absolute and relative extrema. So let's talk about each one. So A is considered to be an absolute minimum. And that's because if you look at the entire graph of f of x, then there is nothing smaller, there is no lower value than what f of a is on the curve. That is the smallest y value. Then we move on to b. Well, b, the y value at b, that's considered to be a relative max. Relative means that it is the largest point or the highest y value on some small interval around b, but it is not the greatest one overall. So that's considered to be a relative or local max. Then we move on to c. C is also a relative minimum or a local minimum. Again, because remember, A was the absolute minimum. And C, although it's small, it has a small y value on a small interval around C, it is not the smallest one overall. Then the graph continues to increase, even though it's got like this little dip here, it still looks like it's increasing all the way till we get to the point of D. And the y value there is the largest value overall. So this is certainly an absolute maximum, but it's also considered to be a relative maximum because it's within the closed interval from A to E. And then finally, we stop at E, and E is none of the extreme values that I talked about. It is not an absolute max or min because there are larger and smaller values than that, and you cannot have a local extrema at an endpoint. So just to repeat that, local extrema, so those would be the relative extrema that we just mentioned here. Local extrema only exist inside of the closed interval of the domain of, I want to say within the domain. So in this case, A and E is my closed interval, and you cannot have local extrema and the endpoints. You can have absolute extrema at the endpoints or inside of the interval, but no local extrema at the beginning and end of the interval. All right, so here's Fermat's theorem. Fermat's theorem talks about critical points. So if f of c is a local maximum or a local minimum, then the value c is considered to be a critical point. A critical point cannot be at the endpoints of a closed interval, so similar to what I explained before. So how do we find a critical point? Well, you're going to use what you already know about derivatives. A critical point represents a local extrema, and it is found by solving f prime of x equal to 0. Remember, f prime of x represents the slope of the tangent line to the curve. And when the tangent line has a slope of 0, it means that we have a tangent line that is horizontal to the curve. Okay, so we can see that here in the picture above. I have a relative or a local max. That means at B and at D, and I have a relative or local min at C. So that means that B, C, and D are critical points. So if I were to sketch what the tangent line would look like at these critical points, it would be a horizontal line. So here you can say that B, C, and D are critical points. Okay, so let's use this information to get some information about a graph. So I have f of x equal to x cubed minus 12x, and we want to find all extreme values on the interval from -3 to 5. Then we're going to use that information to sketch the graph. F of x is what we consider to be a polynomial function. Remember, polynomial functions are defined over all real numbers. There are no restrictions to the domain. It is continuous everywhere, therefore it is definitely continuous from -3 to 5. So based on the extreme value theorem, I should be able to find maxes and mins here. All right, so to help me with that, I'm going to first take the derivative and set it equal to 0 because that will allow me to find critical points. And remember, a critical point could represent a maximum or a minimum value. So I have f prime of x equals 3x squared minus 12 equal to 0. I'm going to use the square root method to solve this. So I have 3x squared equals 12. Divide by 3, you get x squared equals 4. Take the square root of both sides. I get two possibilities. X is equal to plus or minus 2. Plus or minus 2 falls within our interval from -3 to 5, so that's important to consider as well. If your solutions fall outside of the interval, you would ignore those numbers or number. So here on the right, I set up a table just to look at what the y values are, because the y values are going to tell me whether they are the largest value, the smallest value, and information in between. So I start with, I'm putting them in order. I put -3 because that's the beginning of my interval right here. And then I put -2 and 2 because those were the solutions to my first derivative. And then I put 5 because that's the end of my interval. So the second column, I have f of x. And f of x, you're plugging it right in here into your function value. So when x is -3, f of x is 9. When x is -2, f of x is 16. When x is 2, f of x is -16. And when x is 5, f of x is 55. Okay, so observe the y values. Before we even look at the graph, you can kind of answer the question without the graph, but the graph is helpful. So if I'm looking at only the y values here, the f of x column, you can see that my graph goes from 9 to 16, which means it's going up. Then it goes from 16 to -16, meaning it's going down. And then it's going from -16 to 5, meaning it's going back up. When I look at all of the values collectively, the largest value overall is 55. So therefore, that is an absolute maximum. And I know it's an absolute because there's nothing bigger than it. And it can't be local because 5 is at the end of the interval. Similarly, -16 is the smallest value overall. But this -16 is a little different than what we discussed for 55, because that one is an absolute minimum, but it's also a local minimum because 2 is inside of the interval from 3 to 5. Remember, local extrema exist inside of the closed interval. You can also have absolute inside of the closed interval, but the only possibility for the outside of the interval or the first and beginning value can only be absolutes or nothing. All right, so, and then I'm left with 16. Well, since the graph went from 9 to 16 and then down to -16, I know it goes, let's say from 9 to 16, it's going up, then back down again. Well, that means that at 16, I must have a local maximum. Well, let's put this all together in a graph to see if what I wrote here in green makes sense. So I plotted the graph. My y values, or my f of x values, are in intervals of 10, because these numbers are kind of big, and my x values are in are by ones. So when x is -3, y is 9. So that's this first point right here. When x is -2, y is 16. When x is 2, y is -16. And when x is 5, y is 55. So we're here. So when you connect the points that I colored in blue, you see that I have a local max at -216. I have an absolute and a local min at 2, -16. And I have an absolute max at 5, 55. And -39 isn't anything special other than the beginning of the interval. All right, so let's look at this topic with a different perspective. We want to sketch the graph of y equals f of x that satisfies the following requirements. So you have to show that it is continuous from -1 to 5. F of x has an absolute maximum at -1. It has an absolute and a local minimum at 2. And it has a local maximum at 4. So this is one of those sketching problems based on certain criterion. People often have trouble with this. So what I suggest before I actually show you the sketch, because really the best way to do this is to see if you can do it on your own, is I would put the numbers of interest on my number line just to kind of get a feel of what the sketch should look like. So I know it's starting at -1. And I know that at 2, something is going on, right? And then at 4, something else is going on. And then at 5, that's the end. And at 5, I wasn't told that it's an absolute anything in particular. So that means it can't be an absolute max or min. So I have an absolute max at -1. That means nothing can be higher in the graph than what the y value is at -1. So I'm going to draw something kind of high up here to kind of help me. And then I have an absolute minimum at 2, but it's also a local because 2 is inside of the interval. So that means from 1 to 2, it must be going downward. And then I'll have something that's lower than what I had at 1 because it's an absolute minimum. And then I have to have a local max at 4. So from 2 to 4, it has to go up. But remember, you can't go past what you drew for the point at -1. So it must be going that way. And then back down again. Otherwise, that won't be a max. But remember, it can't be smaller than what you put at 2. So it kind of has to have this sort of S shape. So let's see what that looks like on a graph. So it kind of looks like what I drew here. So this matches up with this. Again, where you put the y values don't really matter as long as the y value at -1 is the greatest one overall. The y value at 2 is the smallest one overall. The y value at 4 is a local max, so it has to be greater than what you put at 2, but smaller than what you put at -1. And then 5 can't be anything in particular. So make sure you don't go below the y value at 2. Okay. So let's move on. This time, you're being asked to find all critical points for g of z equal to 1 over z squared minus 4, and identify which critical points are a maximum or a minimum. So g of z is a rational function. Therefore, you have to consider if there are any restrictions on the domain. Well, here there are. You take the equation in the denominator, z squared minus 4, set it equal to 0, and you get that z is equal to plus or minus 2, which means that your domain is all real numbers except -2 and +2, and this is how you write it in interval notation. What that means is that -2 and 2 are critical points, but they can't possibly be maximums and minimums because it's undefined there, but they'll still be important in your graph. So now we have to take our derivative and set it equal to 0. So remember, where your derivative is equal to 0 is where you have these potential maximum and minimum points, because that's where your tangent line should be horizontal. So before I take the derivative, I'm going to rewrite g of z as z squared minus 4 to the negative 1. That will allow me to use chain rule instead of quotient rule. So I take the derivative. So negative 1, z squared minus 4 to the negative 2, times the derivative of the inside, which is 2z. So I'm left with g prime of z is equal to negative 2z over z squared minus 4 to the second power. And that's the equation that we set equal to 0. When you're solving a rational equation, you're really just solving the numerator. And if the solution in the numerator is within your domain, then that's a solution. So I have negative 2z equals 0. 0 is in the domain. And z is so therefore 0 is our critical point. So this is a critical point that has the potential of being either a max or a min, not the 2 we saw here, because the function is undefined there. So since z equal to plus or minus 2 are not in the domain of g of z, then only z equal to 0 is a possible extremum. So to determine if z equal to 0 is a max or a min, we will use what we know about the first derivative. So this next part is an introduction to information you'll hear in future sections that are coming up soon. So recall, so we're kind of reviewing stuff here, recall that when your derivative is positive, the tangent line to the curve goes upward from left to right. So it should be going like this. Positive slope means your line is going that way. G prime positive, which means positive. And that means that your function is increasing. So when your derivative is positive, the function itself is increasing because the tangent line and the curve have to be going in the same direction. When g prime is negative, the tangent line to the curve goes down from left to right. So that's something like this. In this case, g prime is negative, so your curve is going downward, and therefore your function is decreasing. So when the tangent line has a negative slope, in other words, the tangent line is going downward, your function goes in the same direction as the tangent line, and therefore it is decreasing. Therefore, for z equal to 0, we have to check the sign of g prime of z. Is it positive or negative? So notice that here I put on my number line all of my critical points, negative 2, 0, and 2. Even though negative 2 and 2 are not going to be max or mins, I have to be careful not to use them when I'm testing what's going on at 0. So I'm putting them there so that I keep that in mind. So I need to check what's happening to the left and right of 0. And so we use something called a test point. And a test point means that you can pick any value to the left of 0 between negative 2 and 0 to see what the behavior of g prime is. So I'm going to use test point negative 1. So g prime of negative 1. If you plug in negative 1 into g prime of z, you will get that this is and we don't really need to know what the number is, but what you need to know is that it is a positive value. So I indicate that here. I put positive on the number line, and positive means that the graph is increasing. I'll also use the test point to the right of 0, so between 0 and 2, and I'll test 1. And if you plug 1 into g prime, right here, this is g prime, you get that your derivative is negative, which I indicate right here. And a negative means that your function is decreasing. So if you have a graph that is increasing and then decreasing, that means that z equal to 0 is a maximum, and the maximum value is the y value, in other words, g of z. So g of 0, when you plug into the original function, is 1 over 0 squared minus 4. So the maximum value is negative 4, and the maximum point is just 0, negative a quarter. Okay, so now you should try doing the homework for this section. Read the chapter if that helps you. Ask questions as needed. Good luck.